Okay, so we've continued on with a now new type of matter. We actually had two videos talking about liquids, and now we're going to have one here for solids. And this is going to give you just sort of an introduction into different types of solids, how they're structured, and it's also going to focus kind of like the liquid information did on then how that affects melting point and boiling point and things like that. So you'll get to see sort of the original structures and then also the behaviors that result. So to give you an introduction, first off, obviously a solid is made of repeating structural units, and they happen to just come together so strongly that they form this big structure. We're going to see actually two different ways in which these strong attractions are created. One is through actual chemical bonds, and then the other one is through intermolecular forces. So when you start to consider how the structure of the solid is actually put together, whether it's chemical bonds or intermolecular forces, we actually will have four different types that we'll need to talk about. We have what are called molecular solids, we have metallic solids, we have ionic solids, and then finally we have covalent solids. So as these go, generally number 2 and 3, metallic and ionic, are pretty easy to distinguish. It becomes a little tricky when you start talking molecular versus covalent. So definitely listen up for differences there. So to get us started, I am actually going to just front and center hit that molecular versus covalent thing, and we'll do that on this slide. So a molecular solid is going to be held together, as you see here, by intermolecular forces only. So you would have individual molecules or individual atoms, but they're not, these individual molecules are not necessarily bonded together, but it's sort of an intermolecular force that's frozen in place. Water is a great example of this, in fact. When you think about molecular solids, if you're trying to figure out if it's a molecular solid or not, if you can draw a Lewis structure of it and have it be a complete structure all by itself, when it forms a solid, it's probably going to be a molecular solid. Again, if you think about ice, when the hydrogen bonds in water freeze to actually form the ice, it's the hydrogen bonds frozen in place that actually holds that solid together. It's not a literal bond between the oxygens and the hydrogens that's actually holding the structure together. So hopefully that makes sense. The individual atoms within the solid held together by intermolecular forces only. Covalent solids, on the other hand, are held together with covalent bonds. So if we were going to perhaps take individual water molecules and literally covalently bond, that is, one oxygen of one molecule to a hydrogen of a second molecule, then it would be a covalent solid. But that's not how it works. It's an intermolecular force, and it's a molecular solid. So for covalent solids, you have to have individual covalent bonds holding the whole structure together, and it ends up usually forming these long networks or big chains, which really makes it quite strong at that point. They are distinguished by the fact that you can't really draw a correct Lewis structure because it sort of just goes off into oblivion anyway. Diamond and graphite are good examples of this. And at the end of this presentation today, I do have some pictures of diamond versus graphite because those are going to be two that are going to be pretty important to understand to have a visual picture of in your head. So we'll get to that in a second. So again, the difference between these two: intermolecular forces hold the solid together versus covalent bonds hold the solid together. Okay, so moving on to the next two. These are pretty easy to distinguish between themselves. If it's a metallic solid, it's going to be a metal. And it's used, or it is held together by that sea of electrons that we talked about before when we did metallic bonding. Whereas ionic solids, they are held together by the ionic bond, the actual electrical attraction. So any of these examples are a positive cation and a negative anion, and that would be an ionic solid. So these two are pretty easy to determine the difference between. A metal is just going to be that metal atom. The ionic solid will be an ionic formula. But then when you get to the other two, again, that's where the tricky part is. So we're going to talk a little bit about then behavior. So based on what category of solid you might fall into, physical properties are related to the structure. So we'll take a look at melting point to start. And melting point is very simply, in order to melt, you have to overcome whatever force is holding that structure together. So if you're going to melt ice, you have to overcome the strength of the hydrogen bond to remove them enough that the water molecules become mobile again in the liquid form. To break or to melt diamonds, you have to break covalent bonds, not just intermolecular forces. So there's going to be a big difference. So for molecular solids, intermolecular forces are weak. So again, we're talking about, say, solid water, and we want to make it back into water. Intermolecular forces are weak, and so the melting points are relatively low. In contrast, if you look at ionic or covalent solids, you are breaking a literal bond. And breaking bonds is not an easy thing to do, and so the melting points of ionic and covalent solids are generally going to be high when compared to molecular solids. The issue, though, is that when you start to look a little closer, I'm giving you kind of a very, very, very basic trend, but when you look closer, as you can see in this example that I have here at the bottom, these both, sodium chloride and magnesium oxide, these are both ionic solids, and yet the magnesium oxide has a staggeringly more high melting point than does salt. And what the heck is going on here? So the reason for that, we're actually going to continue on and talk about on the next slide. But I need you to recognize that when you compare two ionic compounds, they will both have relatively high melting points, but there's also going to be other factors at work to help you distinguish some of the reasoning behind this. So why does magnesium oxide have such a high melting point and versus sodium chloride? So the reason is there's a difference in ion charges. This is something that's called lattice energy. And lattice energy has to deal with basically the energy held within the crystal structure of this solid. Energy needed to separate a crystal structure into its ions. Well, so we're going back to ions, thinking about ions. It's based on the product of the ion charges. So when you take a look at sodium chloride and magnesium oxide, you would hopefully recognize that sodium chloride, it's a +1 and a -1. And then we have a +2 and a -2. So when you look at the product of those charges, you can actually see that the magnesium oxide product is way bigger in terms of a negative number, that is, as you compare it to sodium chloride. And that in and of itself is going to hold the crystal structure together a lot tighter. You can think of the magnesium oxide basically being stronger magnets. It's a 2+ and a 2- versus a 1+ and a 1-. The higher the charge, the stronger the magnets will hold that solid together. So pretty much what I just said right here. So higher melting points for things that have higher lattice energy. Coulomb's law is something that we have had some time to talk about previous to this, and this is basically just a simple version of Coulomb's law where we understand that greater separation of charge will in fact lead to stronger bonding. So that's the melting point issue. To continue on, so we looked here at some specific issues with melting point and ionic compounds, but as we move on and maybe take a look at metals, some special things that go on with metals. So metals often have very high melting points, but there is considerable variability also in this. So you can see here we're talking about Hg mercury. The melting point is actually -39 degrees Celsius, which means at room temperature it is in fact a liquid. Right next door here, I have tungsten, W. Tungsten is actually used in old incandescent light bulbs. It's the filament that heats up and glows that actually gives you the light out of one of those light bulbs. Its melting point is 3,410 degrees Celsius. Are you kidding? That's crazy. These are both metals, and yet, again, just like the magnesium oxide and sodium chloride example of the previous slide, we're seeing a gigantic discrepancy here between two of the same solid compounds. So, again, sort of what's going on? Well, there's sort of a general trend when it comes to metals in terms of their melting points. It says, in general, melting points are low for group 1A. which I'll show you kind of a picture here as we go along. They're usually low for group 1A and 2A, and as you can see in the slightly darker pink box, my black line is slowly increasing. And then when you get into the middle of the transition metals, you see it sort of tops off and then it begins to drop. So it's considered to be sort of a generalized trend, and it's not something that you're going to be really asked to predict or to really know a lot about. But again, it's just it's sort of a periodic trend we have going on here, and it's something that we experience. And so again, just not all of the same solids are definitely created equal, but you can generally work on trends, general trends that we're kind of talking about here. So focus a little bit more on that. So if I were to give you just the general trend, which I'm kind of alluding to here, just the general trend on melting point, it would look something like this. Your molecular solids, things that are only held together by intermolecular forces, like water, for instance, solid water, ice would be a molecular solid. It's going to have one of the lower melting points. And then it goes up. Ionic and covalent solids usually tend to be next, and the highest melting points tend to be metals. However, please note, this can be a very fuzzy line, in part because of lattice energy, in part because of the metal trends. It's not always easy to predict, but we have something at least generally that we can go off of. So really the biggest issue is knowing the difference between molecular and covalent solids. That really becomes one of the biggest issues. I think, again, metallic and ionic, not so bad. So hopefully this slide will help. For a molecular solid like ice, the interaction between the molecules is intermolecular forces, which are considerably weaker than actual bonds. For a covalent solid, something like diamond or silicon dioxide, which is what makes up glass, the interaction between the carbons or the silicon dioxides, those are all covalent bonds. The covalent bonding extends through the whole lattice structure, and that really gives more strength. So the final bullet point is kind of the overwhelming idea. Thus, a molecular solid usually has lower melting points and boiling points, whereas a giant covalent structure, it tends to be very high in melting point and boiling point both. Okay, so hopefully that slide helps just to solidify the difference real quick. Okay, so next, in talking about physical properties and how they relate to structure, we're going to talk a little bit about hardness. It's pretty clear, I think, what the word actually means, but maybe something you don't recognize is that the hardness of a chemical or of a solid, it definitely depends on how structural units are put together. And in fact, it depends on, as it says here, how structural units can be moved around each other, which is dependent on intermolecular forces. So when you think about something like a metal, remember we've got this sea of electrons, and so we can draw into wires a metal, which is called ductile, or we can hammer it into sheets, which is called malleable. And it's because of the sea of electrons that allows you to sort of flatten it out but still maintain the bonds. Well, in fact, with gold, if you have pure gold, if you bite it, you will leave teeth marks, because what you're actually doing is your teeth are sinking into that metal, and it's pushing the atoms around. So it's changing the location within the solid, but it's never breaking any bonds. So you have what you would call a very soft material. If you can sink your teeth into it and leave teeth marks, that's pretty soft. So the hardness of some metals is definitely considered to be pretty darn soft, in fact. Molecular and metallic solids, they generally have relatively weak intermolecular forces that hold them together, and they end up being considered soft materials, or again, the words malleable, ductile, things like that. A good example of a molecular solid would be a wax. You know that it doesn't take much to melt a wax, and that's in part because you can break those intermolecular forces easily. You can sink a fingernail into solid wax and you can leave an impression. And that's, again, soft, weak intermolecular forces. If you take a look at ionic crystals, like for instance, a big chunk of salt, if you do anything with deer and you get a big salt lick and stick it out in the woods, if you hit that thing with a hammer, it's going to shatter into a bunch of rigid pieces. And that's called being brittle. They are hard structures, and that's because of their strong intermolecular forces between them. When you look at covalent solids, also sometimes called atomic solids, which might be a really helpful thing to recognize, that typically a covalent solid is going to be just like one atom. But with atomic solids, their hardness varies greatly, and that's in part because of the way they're put together. So again, diamond and graphite, I already told you, and I'll tell you again, I will show you a picture of that at the end of this presentation. But diamonds are made of carbon atoms that are stacked in tetrahedrals. So imagine your molecular geometry, that tetrahedral form, and you stack a whole bunch of these tetrahedrals on top of each other, which means that they are bonding side to side and up and down, which creates incredible strength in diamonds. Well, graphite is actually made up of all carbon atoms, just like diamond is, but they're arranged differently. In fact, with graphite, as it says in the parentheses, they're sheets of carbon atoms instead of being bonded side to side and top to bottom, they're just bonded side to side. And so these sheets of graphite, which is what pencil lead used to always be made out of, the sheets will just shear right off. And that leads to a very soft material, as opposed to diamond, which weirdly is made out of the exact same thing. So again, the arrangement of how they're bonded together has gigantic impact. So from hardness, we go to one other physical property that we need to talk about, which is electrical conductivity. You should know well that metallic substances are, of course, electrically conductive, and also ionic substances when they're dissolved in water. So aqueous ionic substances are electrically conductive also. But as it says here, they conduct in different ways and for different reasons. So metals, why do metals conduct electricity? Well, this is something we've talked about, so I don't think it should be a real tricky part here, but they have this delocalized sea of bonding electrons, and so in my parentheses, it's like pool balls hitting in succession, and the last one finally goes in the pocket. So we can conduct electricity all along and pop electrons off the end. For ionic solids, we actually have localized electrons, not delocalized. So we are not conductive as an ionic solid, but when you dissolve it, that's when you break the ions apart, and that's when the electric current can actually travel through. So I want to make it clear that if you have solid salt and you try to make electricity conduct through it, it's never going to happen because the charges are wrapped up within the solid. But if you take a bit of that salt, dissolve it in water, the breaking of those ions will now allow electrical conduction. So it's the only time it would happen. So in talking about a lot of this stuff, all these physical properties and these 4 different types of solids, I believe I gave you this handout, or if I didn't, I'll certainly get it to you tomorrow. But this is a chart that shows you kind of a big summary of everything we've talked about. It lists the type of solid. It talks about what the structural units are made of. It talks about attractive forces, and it gives you examples. On this one, again, type of solid, it talks about what the relative melting point is, hardness and brittleness, and also electrical conductivity. So you can take a couple of moments, if you would, pause the video, read this over, and like I said, I will get you a handout of this tomorrow if I haven't already. Okay, so to finish up here, I have 2 slides left that show you some pictures. First off, when we talk about solids, we do have to sort of consider something about the ions that make up this ionic structure. So this is simply for ionic structures. You can see on the left, the green and the yellow is sodium chloride, and you can see on the right that is cesium chloride. And notice in the box, sodium plus, or the sodium ion, is much smaller than the chloride ion, right? See that? And here in the cesium chloride, we have ions that are approximately the same size. Interesting. Okay, well, let's read in the purple. When ion size varies, 2 like-charged ions contact each other more, which makes a solid weaker. Okay, stop there and look over here. So do you see how these 2 greens, which are chlorines, do you see how they're actually in contact with each other? Whereas here, there isn't as much contact between the blues. And that is possible because the smallness of the sodium, it's going to bring, it's going to bring the chlorides a lot closer to each other, where here there's going to be more space. So it says when ions are similarly sized, less repulsion occurs and the solid is actually stronger. So this is another little thing to keep in mind. If you're comparing two ionic structures, again, we talked already about how magnesium oxide versus sodium chloride, that would really have a difference in the melting point, and that was because of lattice energy, the separation of charge. Well, here, do you notice that the lattice energies would be exactly the same? Because these are plus ones and minus ones, both of them. Cesium is a plus one, chlorine's a minus one. So these have the same lattice energy, but there is going to be a difference in their melting points. The cesium chloride has stronger bonds that are holding it together, which means that this would melt at a higher temperature than this because the chloride ions are a little closer. That's going to repel a little more and be a little easier to pop itself apart. So kind of another idea in terms of understanding how just because you're ionic and just because you have the same lattice energy, it doesn't mean that you're going to have similar melting points. So just another facet to think about. Lots to think about, huh? Definitely. Okay. And then finally, what I've been promising the whole video today, diamond and graphite. So you can see diamond on the left and graphite on the right. Do you see in the diamond how there is it looks like a steel rod connects everything, top, bottom, left to right. The layers are bonded above and below. It is harder. It melts and boils at higher temperatures. Whereas here, you can see that they've sort of shown this blue color to show you sheets, where the carbon atoms are in these hexagon shapes in sheets, and then the red lines that they're showing here, these are representing just intermolecular forces that hold the individual sheets together. So as it says in that black box, the layers can slide across each other, it is softer, and it melts and boils at lower temperatures. So hopefully the visualization helps a little bit also. So that's a little bit on solid structure, understanding some of the basic differences, the types of solids, as well as then how behavior of those solids is impacted is really the biggest part of the story. So that's really it for solids. There's just the one, and after this one, we'll be on to gases. So there you go. See ya.